Unit 9.3 is arcs and central angles. Now, the very first thing you see here is a shortcut study chart for upcoming units. We're fixing to learn a huge handful of rules. And if you're not careful, you'll get all of these rules mixed up. And so to keep you from getting the rules all mixed up, I created this little chart. Now, what you need to know is that as we go through this, see, we've got uh, definition number 80. We got theorem 95, 96, 97, 98. These are theorems that's going to come up, but they're all uh, summarized right here. I'm going to go ahead and teach every bit of this, at least just show you what these things are talking about. And then as you progress through these next few lessons, this will be a good video to come back to and rewind and watch again, okay? So here we go. A central angle. A central angle is an angle whose vertex is the center of the circle and whose sides are radii of the circle. The measure of a central angle is equal to the measure of its intercepted arc. So if that angle is 60 degrees, then that arc measure is 60 degrees. An inscribed angle is an angle whose vertex is a point on the circle and whose sides are chords of the circle. An inscribed angle is equal to 1/2 the measure of its intercepted arc. We could have an angle formed by a chord and a tangent. If we drew a tangent to a circle, I'm going to start that over. I just don't like the way that turned out. I apologize. If we had a chord and a tangent, then the angle formed by that chord and tangent is half the measure of the intercepted arc. So if this arc out here was 300 degrees, then this angle would be 150 degrees. That angle, and I'm going to draw it in red, the angle formed by that tangent and that chord. An angle formed by two chords that intersect inside of a circle is equal to half the sum of the intercepted arcs. If this was 60 degrees and this was 40 degrees, their sum would be 100 degrees. Each of these angles is half of that sum, so they're both 50 degrees. They're vertical, so they've got to be equal. So they're half the sum. Now, let's follow this so far, okay? A central angle, this is the first picture, is an angle whose vertex is the center and whose sides are radii. A central angle is equal to the measure of its intercepted arc. In other words, if the vertex is the center, then the angle is equal to the arc. An inscribed angle is an angle whose vertex is a point on the circle and whose sides are chords of the circle. In an inscribed angle, the vertex is a point on the circle, and it's the angle is equal to 1/2 the measure of the intercepted arc. Notice that when we have an angle formed by a chord and a tangent, the vertex is also on the circle, and the angle is also 1/2 the arc. So an angle formed by a chord and a tangent has a vertex on the circle, and it's also 1/2 the arc. An angle formed by two chords has a vertex that is on the inside, but not the center. If it's on the inside and not the center, then the angle is equal to 1/2 the sum of the intercepted arcs. I'm going to try to write this better. I apologize for the difficulty. So if the vertex is the center, the angle is equal to the arc. If the vertex is on the circle, if the vertex is on the circle, then the angle is 1/2 the arc. If the vertex is on the circle, then the angle is 1/2 the arc. If the vertex is inside the circle, but not the center, then the angle is equal to 1/2 the sum of the arcs, or the average of the intercepted arcs. And then the last scenario, we're just going to make some space because it's got three possibilities. If two secants, two tangents, or a secant, sorry, this is very challenging. My smartboard keeps getting off on me, and I'm about 4 inches off, and I'm trying to draw tangents. Okay. If two secants, two tangents, or a secant and a tangent intersect a circle from a point outside, there's the key, from a point outside the circle, then the measure of the angle formed, the vertex is outside, then the measure of the angle formed is equal to 1/2 the difference in the intercepted arc. The measure of the angle is 1/2 the difference in the intercepted arc. So this angle out here is 1/2 of this big arc minus this little arc. 1/2 arc minus arc. This angle here with the two tangents is equal to 1/2 of big arc minus little arc. Together, those arcs make the whole circle 360 degrees if it's two tangents. If it's a secant and a tangent, then we have two very visible arcs again, but they do connect. So there's one of them. Here's the other one from here to the point of tangency. And so if the vertex is outside, you take half the difference in the intercepted arcs. So we're going to learn a lot of rules, but there's a lot of words in those rules. Central angle is an angle whose vertex is the center and whose sides are radii. The measure of a central angle is equal to the measure of its intercepted arcs. An inscribed angle is an angle whose vertex is a point on the circle, whose sides are chords of the circle. The measure of an inscribed angle is equal to one half the measure of its intercepted arcs. An angle formed by a chord and a tangent to a circle from a point on a circle is equal to one half the measure of its intercepted arc. An angle formed by two chords drawn in a circle is equal to one half the sum of the intercepted arcs. An angle formed by two secants, two tangents, or a secant and a tangent to a circle from a point outside a circle is equal to one half the difference in the intercepted arcs. Now, you really should memorize all of that with understanding, but it's this simple. If the vertex is the center, the angle is equal to the arc it hits. If the vertex is a point on the circle, then the angle is half of the arc it hits. If the vertex is inside of the circle but not the center, then it's half the sum of the arcs. It's the average of the arcs. If the vertex is outside the circle, then the angle is one half the difference in the intercepted arcs. So don't forget, as we go through these theorems, and it seems like a lot of words to deal with, we can simplify this down to what's highlighted in yellow and be successful with understanding the relationship between the angle and the arcs. Okay? So a good place to come back to as we progress. Okay, so now we're really going to start learning these one at a time. A central angle. A central angle is an angle whose vertex is the center and whose sides are radii of the circle. Okay? Examples: angle C, angle BAC. The vertex is center A, the sides are radii BA and CA. Notice that the measure of this central angle is equal to the measure of its intercepted arc. In other words, when the vertex of the angle is the center, then the angle is equal to the arc that it intercepts. Okay? A central angle is equal to the measure of its intercepted arc. That's a rule right here, but it's a rule that we already learned in that chart, right? A central angle is equal to the measure of its intercepted arc. So this central angle 40 is equal to the arc 40. This central angle 72 is equal to the arc 72. This central angle 68 is equal to the arc 68. A semicircle is 180 degrees. We could say that line BE is a straight angle, or angle BAE is a straight angle. This straight angle, angle BAE, 180 degrees, is equal to its intercepted arc, 180 degrees. Okay? We've been talking about all this arc stuff, and we don't even know what an arc is. Geometrically speaking, you know, an arc may be a flash when you own a welder. It may be the sound that a seal makes, but what is an arc geometrically? Well, an arc is a part of a circle. Well, what's that? That's one of those round things. No, that's not what it is. A circle is the set of all points in a plane, a given distance from a given point in that plane. Remember, it's a set of all points in a plane, a given distance from a given point in that plane, and an arc is a part of that. We're making definitions based on things that we know before. An arc is a part of a circle. It is a part of the points in this plane, a given distance from a given point in that plane. It's not all of the points in the plane, a given distance from a given point in that plane. It's a part of those points. An arc is a part of a circle. Now, a minor arc. This is kind of interesting. You know, when we talk about angles, we were kind of maximizing our angle at 180. And then we said, well, half of that is 90, and we're going to call that a right angle. In between these two, we use the word obtuse. And lower than this one, we use the word acute. Well, when we think about arcs, a circle's 360 degrees, so we would max out at 360. So halfway would be 180, and so our subdivisions come in relationship to 180 and 360 on a circle rather than 90 and 180 like it does on a line. Instead of saying acute for the little ones, we say minor on arcs. Instead of saying obtuse for the big ones, we say major. And then for the 180, we don't say straight, we say semicircle because it's half a circle. So classification of angles is based on 0 to 180 degrees. Classification of arcs is based on 360 degrees. So our dividing line, our halfway point on angles is 90, and we call that a right angle. Our halfway point on a circle is a 180, and we call that a semicircle. Less than a semicircle is a minor arc. More than a semicircle, but less than a whole circle is a major arc. Okay? So an arc is a part of a circle. A minor arc is less than halfway around, less than a semicircle. And so BC is a minor arc. From C to D, that's less than a semicircle. It's a minor arc. DE is less than a semicircle. It's a minor arc. You may say, well, you got some more arcs there. Where are you going to get the other ones? Well, you can double up, right? From B all the way to D, that's still less than a semicircle. It looks kind of big, but it's still a minor arc because it's still less than 180 degrees. It's less than a semicircle, so arc BD. Or we could go from E all the way through D to C. That's still less than halfway around, less than a semicircle, and so arc CE is also a minor arc. Now, if you want to find a major arc, it's the rest of the circle when you take away a minor arc. Now, if we want the rest of the circle, we'd have to go here. You may say, well, that's going to be a little hard to name, isn't it? Because they both go from B to C. You can't call them both BC. So we have to name a major arc by 3 letters so that we understand the difference between a minor and a major, because they both start and end at the same point. So when we name the major arc, we're still going to have a BC to begin it and end it with, and you can pick any other point in the middle of that. And so as we go from B to C, we could choose the D or the E to go in the middle to help us name that as a major arc. So major arc would be B, D, C, or B, E, C. Now, if there is a minor arc from C to D, that means there's got to be a major arc from C to D. Well, how do you find it? Well, you go from C to D the long way around. Instead of going from C to D the short way. You go from C to D the long way, and you just grab one of the other points that you run into as you go along there. So we could call it arc CBD or CED. So again, to find all of your major arcs, you just go the long way around from your minor arcs. Okay? If you want to name a semicircle, you find a diameter, because a diameter is going to cut that circle in half. A diameter, by definition, is a chord that passes through the center. I'm going to pause just a second. I can't control this anymore. So if you want to find a semicircle, then you're going to draw a diameter, because a diameter cuts the circle in half. Since both semicircles, the top half and the bottom half, have the same endpoints, then you can't use two letters to name a semicircle, because you wouldn't know which one you're talking about. So you have to use three letters. Well, we can't name the bottom one because there's not a third letter to name it with. We can name the top one. Notice that on the semicircle, we had the endpoints B and E, and then we chose one of the points out of the middle. We just chose C this time. We could have chose D. Okay? All right. So a minor arc is less than 180 degrees. We've already named a bunch of minor arcs. Less than a semicircle, less than halfway around, less than 180 degrees. A major arc is more than 180 degrees. We really should say between 180 degrees and 360 degrees. If we say between 180 degrees and 360 degrees, that does not include the 180 or the 360, but it does include everything between those. Okay? A semicircle is exactly 180 degrees. Okay? A semicircle is exactly 180 degrees. So arc BC, back to the picture. Arc BC is equal to angle BAC, which is equal to 68 degrees. A central angle is equal to the measure of its intercepted arc. Arc CE, that's from here to here, is equal to angle CAE, which is 70 plus 72 plus 40, which is 112 degrees. The sum of those. Postulate 11.1 is arc addition. Now remember, we had angle addition. Just like we had segment addition, angle addition, we have arc addition. Angle addition would say that angle CAD plus angle DAE is equal to the whole big angle, angle CAE, angle addition. Well, arc addition would say that arc CD plus arc DE is equal to that whole big arc CE, arc addition. So we have segment addition, angle addition, and arc addition now. Okay? Postulate 11.1, arc addition. And notice we could also say arc subtraction, right? That whole big arc CE minus arc CD would be arc DE. Okay? And so you can study in your textbook adding and subtracting those arcs and getting the measures. Okay? Okay, congruent arcs. Congruent arcs. Congruent arcs are the same length if and only if they have equal measures or are in congruent circles or in the same circle. Now, why did we say that? Well, this circle right here has a central angle of 90. Therefore, this arc is 90. So arc AB is 90 degrees because it has a central angle of 90 degrees. Well, in this little circle over here, arc FG is also 90 degrees because it's got a central angle of 90 degrees. Does that mean that those arcs are congruent? Same size, same shape? No. It just means they have the same measure. Just because they have the same measure doesn't mean they're the same length. But what about this one right here? This arc DE, is opposite a right angle. That's a central angle. So it has an arc measure of 90, but it came from a circle with the same radius. It's the same size circle. Well, in that situation, these two arcs are congruent. We can say that arc DE is congruent to arc FG because not only are they the same measure, they came from circles that are the same size. Well, what about arc CD? Well, it's in the same circle as arc DE. So arc CD is congruent to arc DE because it has the same measure as arc DE and it's in the same circle. Arc FG is congruent to arc DE because it's the same measure as arc DE, but it's in the same size circle. Arc AB has the same measure, but it's not congruent because it came from a circle of different size, you see. So congruent arcs are the same length if and only if they have the same measure and they are in the same circle or in equal or congruent circles. That would be circles that have this equal radii, okay? So if the arcs are going to be the same length, meaning they're congruent, then they would have to come from circles that are equal in size or from the same circle and also have equal measures. So the lengths are equal if and only if the measures are equal and they're in the same circle or in equal circles, okay? Congruent arcs. All right, that brings us to the 9-3 daily work. It says name 4 central angles. Remember, a central angle is an angle whose vertex is the center and whose sides are chords, and whose sides are radii. The vertex is the center, the sides are radii. So angle EQF would be a central angle. And you could name the others. If you want to name a minor arc, then what we want to do is think about a diameter. A minor arc would be less than a semicircle, and a diameter makes a semicircle. So one minor arc would be from F to E because it didn't make it all the way around to the end point of that diameter. So arc FE is a minor arc. Now, if arc FE is a minor arc, that means that there's a major arc that goes from F to E the long way around. But we have to name it by 3 letters. When we go the long way around, we run into H and we run into R. You can use either of those two to put in the middle. I'm just going to use H. And so if arc FE is a minor arc, then arc FHE is a major arc. Okay? It says name 4 semicircles. To find a semicircle, you first find a radius. A radius will create a semicircle. The endpoints of the chord of the semicircle are the endpoints of the diameter. I'm trying to draw this. I apologize. I'm trying to do a good job here. So that would be a semicircle. We have to use 3 letters because there's one on top and bottom that starts at F and ends at R. So if we go around the top, a point in the middle was E, and so we put E in the middle. So arc FER is a semicircle, and you can name the rest. Now look at all these questions, 5 through 19, 5 through 21, 5 through 21. Look at that. All I have right there is this thing drawn with a 40-degree angle. Now, how am I supposed to find all of that stuff? Well, that comes from some theorems. Remember when we were drawing those pictures and we said, okay, when we're trying to inscribe a circle, a triangle, inscribe a right triangle, inscribe an acute triangle, inscribe an obtuse triangle, inscribe a rectangle, a rhombus, and a square. And we said this really gets to be all about the diagonals. And we're supposed to know the properties of the diagonals of a rhombus, rectangle, and square. So when we get enough information about the rhombus, about the diagonals, we can figure out what kind of figure that is. Watch this, okay? Here's what all we can figure out from that. We know that QR, ER, FR, and QH are all radii of the circle. Now, if the radii, they're all equal, that thing has 4 equal radii pieces, or 4 equal diagonal pieces. Now, in what type of a figure do the 4 diagonal pieces come out to be the same? For that to happen, they would have had to have been equal to start with and bisect each other. Now, if the diagonals bisect each other, that proves that it's a parallelogram. But if they're equal and bisect each other, it proves that it's a rectangle. So we know that this is a rectangle because the diagonals are equal and bisect each other. Okay? Now I'm going to get those marks out of the way so I can put some other stuff in there. If that's true, then that means that the angle at E is 90 degrees. I'm going to have to make my pen right here, just a second. It means that the angle at E is 90 degrees. The angle at R is 90. The angle at F is 90. And the angle at H is 90. Okay? Also, all of these triangles in here are isosceles triangles. Now, I think what I need to do is just try to draw this thing a little bit bigger. So I'm going to white out some stuff out here so you can know what I'm talking about. Okay? I'm just going to try to blow this up. Let me blow up just one piece at a time. What I'm drawing here is EF. And Q. These were equal because they're all radii, and this is 40 degrees. Now, what I have is an isosceles triangle. If two sides of a triangle are equal, then the angles opposite those equal sides are equal. So that little angle at E is equal to that little angle at F. The sum of the angles of a triangle is 180 degrees. 180 degrees minus 40 degrees leaves 140 degrees. If you divide that by 2, you get 70 degrees apiece for this little angle at E and the little angle at F. Now, the whole big angles were 90, so let's see if we can fit this in here. This little angle is 70, and this little angle is 70, and this little angle is 70, and that little angle is 70. Well, the whole big angle was 90, so 90 minus 70 is 20, so that's 20, and this is 20, and this is 20, and this is 20. And a straight angle is 140. A straight angle is 180. That's interesting, isn't it? A straight angle is 180 degrees. If we take that 40 degrees away, we would get 140 degrees for this obtuse angle in here if I can get some numbers in there. This is getting so small you can't hardly see it. Okay? So I'm going to make that bigger. Here's my rectangle. Bear with me, please. We began by saying that these are all radii of the circle, therefore they're equal. Since we had 4 equal diagonal pieces, we knew it was a rectangle. This little angle is 40 degrees. Okay, so we had that angle was 40 degrees. We know if this is 40, then this one over here is 40 degrees because vertical angles are equal. We know a straight line's 180, so 180 minus 40 leaves 140 degrees for this angle, which means this one's also 140 because they're vertical. Like we said a while ago, the sum of the angles of a triangle is 180. 180 minus the 40 leaves 140. Divided by 2 would be 70 degrees apiece for these. Those are equal because it's an isosceles triangle. If those are both 70, these are both 70 for the same reason. Each angle of the rectangle was 90. So 90 minus 70 would leave 20 for this little angle, and 20 for this little angle, and 20 for this little angle, and 20 for this little angle. That all came from the properties of a rectangle. And again, we knew it was a rectangle because the diagonals are equal and bisect each other. Now, the arcs, this arc here is equal to this central angle. So if that arc is 40, if that angle is 40, that arc is 40. This arc is equal to this central angle, so it's 140. This arc is equal to that central angle, so it's 40. This arc is equal to that central angle, so it's 140. So we have all of the arc measures, and we have all of the angle measures. That was all based on our rectangle properties, triangle properties, straight angle properties, and arc angle relationships. So, arc EF, here's my E, F, H, R, and Q in the middle. Arc EF is 40 degrees. I like to fill in the whole picture and then answer the question, see? Arc ER, 140 degrees. EFR. EFR would be the long way around. From E to F is 40, plus 140 is 180, plus 40 is 220. From E to F to R, 220 degrees. Okay? You can fill in the rest. Number 19, parallelogram ERHF is a rectangle. We knew that because we had 4 equal diagonal pieces. That meant they bisected each other, which made it a parallelogram. If they're equal and bisect each other, that makes it a rectangle. If EF is equal to 5, and ER is equal to 12, then what would you do to find FR? Well, we know that that angle's 90, so we could do the Pythagorean theorem, right? So don't forget about your right triangle rules also, okay? The diagonals are perpendicular. See the 90? These are all radii, so they're equal. The diagonals bisect each other. That makes it a parallelogram. They are equal and bisect each other. That makes it a rectangle. They're perpendicular, equal, and bisect each other. The fact that they're perpendicular makes it a rhombus. The fact that they are equal and bisect each other make it a rectangle, and there's only one kind of a rectangle that's a rhombus, and there's only one kind of a rhombus that's a rectangle, and that's a square. So that must be a square. And in a square, Both pairs of opposite sides are parallel. Both pairs of opposite sides are equal. Both pairs of opposite angles are equal. The diagonals bisect each other. Each diagonal bisects a pair of opposite angles. The diagonals form congruent triangles. The diagonals are equal. The diagonals are perpendicular. All four sides are equal. All four angles are right angles. Tons of properties of a square, and you'll be using all of those properties to answer all of those questions. Okay? And we're going to let you answer all those questions. And that finishes up daily work 9-3, the part that we're going over anyway.